How does one study what one cannot see? Over the centuries, investigators interested in the structure of the atom have worked pretty much in the dark. Until the day that Henri Becquerel developed a piece of photographic paper on which had been placed a uranium compound. The discovery of radiation led Ernest Rutherford to devise the first tools with which to probe the atom directly. From the newly discovered element polonium, Rutherford identified emanations which were absorbed by a lead box. A hole allowed this radiation to escape, and some could be detected on a screen. A strong magnetic field bent one set of rays slightly in one direction, and another set of rays strongly in the other. This indicated that the rays consisted of particles which had both mass and charge. Rutherford dubbed them alpha and beta particles. The alpha particle, being fast, massive, and positively charged, seemed the ideal probe with which to penetrate the atomic surface. Rutherford's probe consisted of a point source of alpha particles, a sheet of gold foil, and a zinc sulfide detection screen. Rutherford found that most of the alpha particles passed through the gold foil with little or no detectable change of direction. Occasionally, however, the detection screen showed that a particle had been deflected significantly. More rarely yet, a direct rebound could be detected, an event which, as Rutherford described it, was like firing a large naval shell at a piece of tissue paper and having it bounce back and hit you. These findings indicated to Rutherford that much of the gold foil must, at the atomic level, be empty space. But what in the foil was causing a small number of the alpha particles to be scattered from their original line of motion? One possibility, the alpha particle was colliding with some other particle, in the same way that two hard billiard balls collide. This kind of collision produces a distinctive pattern. Although Rutherford could not see the individual tracks, he intercepted them with screens at many different positions, until he built up an idea of the actual pattern produced. And it was quite different from our earlier pattern of billiard ball collisions. So Rutherford looked to Coulomb's law for an explanation. The force of repulsion between two particles with the same charge increases as distance decreases. Is it possible that the positively charged alpha particles were being repelled by a nucleus of positive charge within the gold foil? Let's consider what would happen to an alpha particle on a direct head-on collision course with such a positively charged nucleus. We will show only the force exerted on the alpha particle. As the alpha particle approaches the nucleus, the force acting on it rapidly grows larger, causing the alpha particle to slow down, stop, then accelerate back in the direction from which it came. Let's look at it again. What about an alpha particle which is on a path which would take it just past the side of the nucleus? Consider first if no electrostatic force were acting. But if the nucleus carries a positive charge, the electrostatic force will grow rapidly as it did before. Since the alpha particle is not on a direct head-on collision course, the electrostatic force exerted by the nucleus affects not only the speed of the particle, but also its direction. Let's look at it again and stop the action completely. The force of repulsion can be broken into two components. The component parallel to the path of the alpha particle slows it down, while the other component, perpendicular to its motion, changes the direction of the particle. A characteristic curve is traced as one charged particle interacts with another. By assuming the existence of a positive charge, Rutherford was able to mathematically calculate a scattering pattern which matched those observed in his gold foil experiment. What was this mysterious positively charged particle? Well, Rutherford knew that the closer an alpha particle came to the mystery, the greater the angle at which it was repelled. So he was able to estimate the distance of closest approach. He found it to be astonishingly small. The positively charged particle at its center could have a radius no larger than 3 × 10⁻⁻14 meters. Even if the tiniest dot on this screen represents its nucleus, the atom itself is gigantic in comparison. It was Rutherford who coined the term nucleus and applied it to this tiny central core lost in the vast space of the atom. He proposed a structure for the atom which mimics, in miniature, the solar system. The tiny, heavy nucleus is orbited by lighter electrons. The force of attraction between the electron and the nucleus prevents the electron from flying off into space. But it is not great enough to cause the moving electron to spiral into the nucleus. Rutherford's model represented a significant step forward in our understanding of the atom. But in the end, it presented problems. Classical physics theory predicts that an accelerated charge will produce electromagnetic radiation, a form of energy. Well, an electron moving in a circle at a constant speed is an accelerating charge. And yet, if it continually radiates electromagnetic energy, it is obviously losing that energy. This should cause it to drop towards the nucleus, where it will rotate more frequently, thus increasing the frequency of the radiation. But this kind of increasing frequency shift is never observed. Eventually, the electron should lose so much energy it would spiral into the nucleus. But in reality, most atoms are very stable. The Rutherford model, if it was to survive, needed help urgently.